Good morning, everyone. Very good morning. Shall we begin the session? In the today's class, yes, we are going to cover the chapter number 9, that is the virtual memory. So shall we begin or shall we wait for others? Okay, so wait for others. Alright. Now let's talk about the first part, that is the physical and the virtual addressing. The address space, then VM as a tool for the caching, then VM as a tool for memory management, and then VM as a tool for memory protection, then address translation, then there is a case study for the Intel Core i7, then memory mapping, dynamic memory allocation, garbage collection, common memory related bugs in the C programs, and then there is a summary. Now, whatever the processes in a system, whatever the processor that is used, that shares the CPU with the various, we can say the memory, with other memory also, the processes also. However, sharing the main memory possesses some special challenges. As the demand on the CPU increases, processes slow down. So whenever there are multiple processes, so automatically the speed will be goes down in some reasonable smooth way. But if too many processes needs too much memory, then some of them will simply not be able to run this one. And when the program is out of the space, it is out of the luck. And memory is also vulnerable to the corruption because there is no corruption in the memory. In order to manage the memory more efficiently with a few errors, with a smooth reliability, modern system also provides instruction of the main memory, that is known as a VM, virtual memory. So VM is, yes, virtual memory that physically does not exist, but its existence is available within the process. Yes, to perform the with the area various errors with the efficiently and fewer errors. And virtual memory is an elegant interaction of the hardware exceptions, hardware address translation, main memory, disk file, and the kernel software that provides each process with a large, uniform, and the private address space. Whatever the address space, whatever the capabilities we are using out, so that is used with the mechanism, that is used with the scenarios available for the cache, for the address space that is stored on a disk. Keeping only the active areas in the main memory and transferring back the data, that is back and forth between the disk and the memory whenever it is needed. And it also simplifies the memory management by providing each process with a uniform address space. Third, it protects the address space of each process from corruption by other processes. So whatever the process that is carried out, so that protects the address space of each and every process from the corruption. And virtual memory is one of the great ideas in the computer system. The main reason for its success is that it works silently and automatically without any intervention from the application programmer. Since virtual memory also works behind this one, so there are multiple reasons why we are going to study the virtual memory. First one is virtual memory is central. So virtual memory pervade all level of the computer system, playing the key roles in the design of the hardware exceptions, assembler, linker, loaders, shared objects, files, and the processors. And understanding the virtual memory, whatever the virtual memory we are using, that help you better understand how the system works in general. So first it is the central, so it pervades all level of the computer system, playing key roles in the design of the hardware exceptions, assembler, whatever the assembler key areas we are using, linkers, loaders, shared objects, files, and the processes. And understanding the virtual memory will help you better understand how the system works in a general. So virtual memory is central. Then virtual memory is powerful. It is powerful in the sense it provides powerful capabilities to create and destroy the chunks of the memory, whatever the chunks we are using. So this provides the chunks that is available over here. Then virtual memory is dangerous. Application interact with the virtual memory. Every time they reference a variable, dereference a pointer, or makes a call to a dynamic allocation package such as a malloc. So virtual memory is dangerous in the sense it is using with the malloc function, calloc function. And if it is used improperly, applications can suffer from perplexing and also use memory-related bugs. For example, a program with a byte pointer can crash immediately with the segmentation fault or the protection fault, and that can run silently for the hours before the crashing. Now, first is physical and the virtual addressing. What is the physical address? Whatever the address or the machine have, that is known as the physical address. Whatever the whatever the logical address that is used. So this provides the CPU to access the memory. Yes, memory with the use of the physical addressing that shows an example in the context of loading instructions. And when the CPU executes the load instruction, it generates an effective physical address and passes it to the main memory over the memory bus. And the main memory fetches the 4-byte word starting at the physical address 4 and return it to the CPU that stores it in a register. And every time or early PCs also uses the physical addressing system such as the digital signal processors, embedded microcontrollers, and crazed supercomputer that continue to do so. However, modern processor also uses a form of the addressing that is known as a virtual addressing. And with virtual addressing, we are using with the virtual address that is converted into the appropriate physical address before being sent to the memory, and the task of converting a virtual address to a physical one is known as address translation. So whenever we convert virtual address to a physical address, that is known as address translation. And like the exception handling, address translation is also requires the close cooperation between the hardware, CPU, and the CPU, hardware, and everything that is available over here. So this is the order set of the non-negative integer addresses. Whatever the address space is an order set of the non-negative integers value or addresses we are taking out. And this address space are consecutive. We can say that it is a linear address space, and that is used for the linear address space also in a system that is using the virtual memory. And CPU also generates a virtual addresses from an address space of n to n addresses known as a virtual address space. And the size of an address space is also characterized by the number of bits that are needed to represent the largest address. For example, if I'm talking about the virtual address space, then n addresses is known as an n-bit address space, and the modern system typically supports either 32-bit or the 64-bit virtual address spaces. A system also has a physical address space that corresponds to the physical memory. For example, this is one of the scenarios. This is 0, 1, 2 till m minus 1. That is, m is not required to be the power of the 2, but to simplify the discussion, we will assume that m equals to 2 power m. That is not required to the power of 2, but to simplify the discussion, we are using this one. That is available with the virtual memory, that is available with the physical memory, that is VP0, VP1, unallocated, cached, uncached, unallocated, cached, uncached, cached, uncached. This is empty set, empty set, empty set, and there are multiple virtual pages also that is also stored on the disk. So there are virtual addresses, there are physical pages, that is the VP. This is the main idea, basic idea of the virtual memory. And each byte of the main memory has a virtual address chosen from the virtual address space and a physical address chosen from the physical address space. That is available with 2 power 20, 2 power 30, 2 power 40. That is, this starts from the kilo, then megabyte, then giga, then tera, then peta, then exa. This is 2 power 10, 2 power 20, 2 power 30, 2 power 40, 2 power 50, 2 power 60. then VM as a tool for the caching. So conceptually, a virtual memory is organized as an array of the n contiguous byte-sized cells stored on a disk, and each byte has a unique address or the unique virtual address that serves as an index into the array, and the contents of the array on the disk are cached in the main memory that is available with the physical address that is available with the p bytes in the size, that is physical address also referred as the page frames. And at this point of time or any point of time, a set of the virtual memory is partitioned into the three distinct subsets. One is unallocated, that means the pages are not allocated yet and that is not available yet, or used by the VM system. Then cache allocated pages that are currently cached in the physical memory, then uncached. Then this is a memory that is available with the cache. There are three terms or three cache memories, L1, L2, L3, that is between the CPU and the main memory, and the term DRAM cache to denote the VM system cache that caches virtual pages into the main memory. And the position of the DRAM cache in the memory hierarchy has a big impact on the way that is it is organized. And recall that DRAM is at least 10 times slower than the SRAM, and the disk is about 100,000 times slower than the DRAM. Therefore, misses in the DRAM caches are very expensive compared to the misses in the SRAM cache, because DRAM cache misses are served on a disk or from the disk, while SRAM cache misses are usually served from the DRAM based main memory that is slower than reading the successive bytes in the memory. Then page table, that is a way to determine if a virtual page is cached somewhere in the dynamic RAM. If so, the system must determine which physical page it is cached in. If there are missed, the system must determine where the virtual page is stored on a disk. Select a victim page in the physical memory and copy the virtual page from the disk to the DRAM. That is used with the victim page that is available with the page table, null values VP1, VP2. That is the page table entries, that is also known as a PTE, valid bit, dynamic RAM. Yes, valid bit is set to 0. Addresses field indicate the start of the corresponding physical page in the DRAM where the virtual memory is cached up. Now this figure shows what are the various references that is to be word in VP2 as a hit. This is the virtual address, physical page number or the disk address, then physical memory, that is a DRAM, then virtual memory, that is a disk, then memory resident page table. So memory resident page table in the sense whatever the DRAM capability that is available, that is covered with the PPC and PP3. Then next is page hits. So consider what happened when the CPU reads a word of the virtual memory contained in VP2 that is cached in the DRAM. And using this technique, we will describe in detail the address translation hardware uses the virtual memory that is used as an index to locate the PTE2 and read it from the memory. And since the valid bit is also set, so the address translation is done in the cache memory between the devices to construct the physical address. And whenever there is a miss, that is known as a page fault. So there is a miss in the sense virtual memory does not occupy the CPU, that is known as a miss. That is also known as a page fault that shows the state of, for example, page table before the fault, and CPU is referenced in a word in VP3 which is not cached in the DRAM. And this translation also reads out the PT3 from the memory that infer from the valid bit. And VP3 is not cached out and triggers as a page fault exception. Then physical page number on the disk address, physical memory, main memory or main resident page table, virtual memory, physical page number on the disk address, physical memory. That is used also known as the swapping or the paging, that is